Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
Students, the topic for today's class is the efficiency of transformer. Okay, so today we are going to calculate the efficiency of transformer. Now let us define efficiency first. Now, even if you don't consider transformer, what is the meaning of efficiency? What does this word convey? Now basically efficiency is that you are supplying X amount of input to a device and how much of this input is getting converted into output. That is the efficiency. Fine. Now suppose this is a device or a system. Okay. And X is the input. Now we are getting Y as the output. Okay, then what will be efficiency? Efficiency is represented by letter eta. Now it is going to be that this much output is generated after giving this much input. Got it? Yes. So this is a generic definition. Now if you talk about efficiency of transformer, I would say that efficiency of the transformer is the ratio of output power to input power. Okay. Now we also know that here the input power is responsible for generating output power plus losses. Am I right? Which losses? Majorly two losses. The iron loss or the core loss and the copper loss. Fine. Correct? Because input power gets converted into output power plus iron loss or core loss and copper loss. Fine. So eta is given by output power upon input power. Input power can be replaced by output power plus losses. So my eta becomes output power upon output power plus iron loss plus copper loss. So eta will be represented by output power, which is V2I2 cos phi 2. That is output power. How do we represent output power? V2I2 into cos phi 2 divided by output power. Output power is represented by V2I2 cos phi 2 plus iron losses and copper losses. Now these are two different nomenclatures, like we can represent it by Wi or WCU or PI, PC. No, as I said that at various places we use various nomenclatures. Even if I write this, it is the same. Fine? Yes? So the output power of transformer is specified here. Okay? Whereas cos phi 2 is nothing but the power factor. Okay? Yes. So what I'm going to do is, I'm going to convert this into kVA. Now in last lecture we understood what is kVA. Correct? Kilovolts ampere. So this output power will be converted into kVA instead of watts. So it becomes V2I2 upon 1000. So what is going to be my total output power? Now V2I2 upon 1000 represents kVA. Correct? And it will be multiplied by power factor. Fine? kVA is the standard unit to represent output power. Okay. Now what we are going to consider is, generally we consider the condition of full load. Now suppose full load is not applied. Okay. Then we will consider x to be the fraction of full load. It means suppose the full load condition was 100 and I am applying 60. So what fraction I am applying? It is 60 upon 100, which becomes 0.6. So this becomes my x. Okay. Not always we apply full load condition. So what happens is we apply x, which is the fraction of full load. I hope it is clear after taking these examples. Okay. That full load condition was 100. We are not applying 100. We are applying 60%, which makes it say 60. So 60 upon 100, which makes it 0.6. We may apply full load. We may not apply full load. X can be smaller than 1 or it can also be equal to 1 in case of full load condition. Fine. So let us write the general equation that let x be the fraction of full load. So the efficiency of the transformer with respect to x will be represented by this. So eta at x will be x multiplied by the output, upon again x multiplied by output, and remember this output is full load output. Okay, so this output is full load output. Fine. Again this output is full load output. Multiplied by, so you multiply this full load output by x. Then you have Pi plus here you have x square Pc. Now remember your iron loss does not depend on current. So there we will not get x. So it is multiplied at copper loss, x square. Fine. Now let us arrive at a condition which is maximum efficiency. Now whenever we are operating any device, whenever we purchase something, what do we require? We require that it should give us maximum output, isn't it? Right. So we also want maximum efficiency from transformer. So when we plot the graph, for efficiency with respect to output current, we notice that efficiency increases by increasing the output current till particular point, and this point is called maximum efficiency. Okay, and this corresponding current is the maximum secondary current. But after a particular point, it starts reducing. It means that we should operate our transformer if we want to get the maximum efficiency, then we have to operate it at this condition. Beyond this, if we further increase the current, then efficiency would reduce. Fine, okay. But then let us understand this with respect to all these equations. Okay, so again we will be writing the efficiency equation. So it is the same equation. Fine. So copper loss will be represented by I square R loss. Okay, so it is, we are talking about the secondary side. So it has I2 square RES, and that is the equivalent secondary resistance. Fine. Now what we have done is, now we will divide this equation by I2. Okay, after doing this, we get this equation. We have divided the equation by I2. So we got this equation. Fine. Now why did we do that? Now let us compare this efficiency and this equation. Okay. Now if you see V2, the voltage will be constant, right? Cos phi 2, again it is not affected by load condition. So again it is constant. It means what? That this efficiency depends on one factor. Which factor? What is that parameter? That parameter is I2. It means that my efficiency depends on I2. It does not depend on V2 as it is constant. It does not depend on cos phi 2. Again it is constant. Fine. So for achieving the maximum efficiency, what is the procedure? We will be differentiating the equation, and lastly we will be equating it to 0. So we will differentiate this efficiency equation with respect to I2, and then we will equate it to 0. Fine? Okay? Yes. See, the same thing is written, that the value of the terminal voltage is constant. So for a given power factor, transformer efficiency depends on the load current I2. Correct? So it is maximum when its differentiation with respect to I2 is equal to 0. Fine. So we will differentiate it and we will equate it to 0. So what we will do is, we will differentiate this with respect to I2 and then we will make it to 0. We will equate it to 0. Fine. So if you see, this is constant. See, this is constant. So differentiation of this is going to be 0. Here we have it in denominator, I2. So differentiation would be minus I2 square. Correct. And here we have I2. So differentiation of I2 with respect to I2 will be 1. So we will have RES left out there. So see, this is the differentiation. The first term becomes 0. The second term has minus 1 upon I2 square, and Pi was already there, plus differentiation of I2 with respect to I2 became 1 and RES was already there. Fine? Yes. Now what will be the next term? Next equation? We will take this to the right hand side because this is a negative term. Correct? So we got this equation. Okay. How did we get that? Because RES becomes equal to Pi upon I2 square. So we simply did the cross multiplication. Okay. So this is taken to here. Fine. What is this I square R? This is nothing but copper loss. What was Pi? It was iron loss, right? So what is the condition? What is the condition? Condition says that you will get the maximum efficiency when copper loss is equal to iron loss. This is the condition. So transformer will give the maximum efficiency when the copper loss is equal to the iron loss. Fine? Okay. So in the earlier equation, what we will do is, where copper loss was written, we will replace it by iron loss. Okay. So second and third term they combine together as 2 pi. So this becomes my maximum efficiency. And from equation 2, from this equation, we can get the value of I2. Okay. Now again we will be taking X amount of full load kVA, because not always we go for full load current and full load rating. So we will consider that X amount of full load is taken. So X is the fraction of full load kVA. Okay, at which the maximum efficiency occurs. Then copper loss will be proportional to the current, and it is power, so it is proportional to square of the current. So X is also squared. So when we take full load condition, this equation is applicable. Okay, when we take full load condition, this equation is applicable. But when we take X amount of this, next condition comes. So copper loss becomes X square PC instead of only PC. But iron loss is not affected by that. So iron loss will remain the same. So in this condition, where we take X amount of full load rating, the condition becomes X square PC equal to Pi. Fine. So from that condition, I arrive at this, that X equal to square root of Pi upon PC. Similarly, we get the maximum efficiency as this. Okay. So we will put the equation, the value of X from equation 3 into equation 4. So here we get the maximum efficiency. Okay, which is square root Pi upon PC into full load kVA. Fine. So when we put this value, the maximum efficiency comes out to be this. So we have to remember this equation. That maximum efficiency will be full load kVA multiplied by the square root of iron loss upon copper loss at full load. Okay, I hope this is clear to you. Yes. So now let us see what happens to the load current. Okay, now load current at eta max is given by I2 max, and it comes out to be the full load secondary current, multiplied by the same ratio, okay, which is square root of, here we took Pi, right? So here also I will write Pi only. At full load. Okay, this is again a very important parameter. Fine. Okay, all other things we have already calculated. So what did we learn? We learned today that efficiency of the transformer is the ratio of output power to input power, and we also learned that condition for maximum efficiency is when core loss becomes equal to copper loss, and we derived certain equations. Fine. So we come to the end of this lecture. We shall meet in the next lecture. Till then, keep studying.